Well, welcome back to our class on discrete mathematics, focusing on discrete structures, primarily looking at things from a computer science point of view. And as we continue on in this material, what we're going to be talking about today is looking at relations. And some of this will be fairly familiar to you, but we're of course going to be extending it for discrete mathematics and numbers theory to be thinking about some things from that point of view. So here is a synopsis of what we'll cover in the chapter. There are several sections that we will not have in the lecture notes that you can go to Rose and refer to, but we at least have 5 things that we'll be looking at. So relations and their properties, representing relations, equivalence, relations, and partial ordering. But I'll give a little bit of a synopsis of the whole chapter here before we go on. So relationships between elements of every set occur in many contexts. Every day we deal with relations such as those between a business and its telephone number, an employee and his or her salary, a person and a relative, and so on. So those may be some things that are easy for you to get your head around what relations are. In mathematics, though, we study relations such as those between a positive integer and one that it divides, an integer and one that it is congruent to modulo 5, a real number and one that is larger than it, a real number x, and the value f of x, where f is a function, and so on. Relationships such as that between a program and a variable it uses, and between a computer language and a valid statement in its language, often arise in computer science. Relations between elements of 2 sets are represented using the structure called a binary relationship, which is just a subset of the Cartesian product of the sets. Relations can be used to solve problems such as determining which pairs of cities are linked by airline flights in a network, or finding a viable order for the different phases of complicated project. We will introduce a number of different properties binary relations may enjoy. Relationships between elements of more than 2 sets arise in many contexts. These relationships can be represented by n-ary relations. We're not going to go into detail here, but I'll just mention it for now. Such relations are the basis of the relational data model, the most common way to store information in computer databases. We will introduce the terminology used to study relational databases, define some important operations of them, and introduce the database query language SQL. We will conclude our brief study of n-ary relations in databases with an important application from data mining. In particular, we will show how databases of transactions represented by n-ary relationships are used to measure the likelihood that someone buys a particular product from a store when they buy one or more other products. 2 methods for representing relations using square matrices and using directed graphs consisting of vertices and directed edges will be introduced and used in later sections of the chapter. We will also study relations that have certain collections of properties that relations may enjoy. For example, in some computer languages, only the first 31 characters of the name of a variable matters. This was a limitation of some of the things that Microsoft had for a while. The relation consists of ordered pairs of strings in which the first strings had the same initial 31 characters as the second string is an example of a special type of relation known as equivalence relation. Equivalence relations arise throughout mathematics and computer science. Finally, we'll study relations called partial ordering, which generalize the notion of the less than or equal to relation. For example, the set of all pairs of strings of English letters in which the second string is of the same as the first string or comes after the first in dictionary order is a partial ordering. So that's a little bit of a synopsis of what we're going to cover, but let's get into the first section. And this is what we're going to be talking about, relations and functions. and some other stuff. So the most direct way to express a relation between elements of two sets is to use an ordered pair made up of two related elements. For this reason, sets of ordered pairs are called binary relations. In this section, we introduce the basic terminology used to describe binary relations. Later in this chapter, we will use relations to solve problems involving communication networks, project scheduling, and identifying elements and sets with common properties. So relations and functions, properties of relations, we'll get into several types of characteristics, reflexive, symmetric, and antisymmetric, and transitive, and then how we can combine those relationships. So let's go through a couple of definitions, and I'll try and keep this at a high level. So a binary relationship from R is a set of A to a set B. And so a binary relationship from A to B is a set of R of ordered pairs where the first element of each ordered pair comes from A and the second element comes from B, where A comma B belongs to R and is said to be related by R. Binary relations represent relationships between the elements of two sets. And you can see there can be one-to-many relationships. And so this is where it's different than a function. And you can see this here. Relations are more general than function. The functions are related when exactly one element of B is related to each element of A. Okay, here we have a binary relation of R on a set A is a subset of AXA, or relations from A to A. And so relations from a set A to itself are another thing that are special interests. And so this is what we're trying to get at. And we're going to have some ways of graphically showing some information that I think might be helpful to help you grasp this. So if A, B, and C are in A, we can have all these things where one element is pointing to another element within that set A. So how many relations are there in a set A? I'll let you walk through the solution, but the relation that has n squared elements when A has n elements. And so that's one of the things that we can be considering for that. So it's not hard to determine the number of relations on a finite set because a relation on a set A is simply a subset of A cross A. And so this is something that we can be thinking here. But the ones that we're showing are relations are on an infinite set, and each of these relationships is an infinite set. So that's something that we want to be thinking about as well. We can talk about finite or infinite sets if we phrase it in a well understood way. Okay, what about reflexive relations? There are several properties that are used to classify a relationship on a set. We will introduce the most important of these here and over this chart and the next handful of charts. In some relations, an element is always related to itself. We see that a relation on A is reflexive if every element on A is related to itself. So that's what we're trying to capture here. And we have an example that I won't walk through just to keep this at a high level. Okay, what about symmetric? So we can be thinking of symmetric as it's written here, but in other words, a relation is symmetric if and only if it is related to B, implies that B is related to A. So you can go from A to B and B to A. That's what this is trying to reply. We can also have something called anti-symmetric. So relation A on set, relation R on set A such that for AB is an element of A, if A comma B is an element of R and B comma A is an element of R, then A equals B is called an antisymmetric relationship. And so this is another thing that we can be utilizing. We also have the transitive relation. And so we have the definition as it's laid out here on the top of this chart. Let R be the relation consist of the pair AX of students in your school. So I'm just going to talk about this by example, where X has taken some credit where X student has taken more credits than Y. Suppose that X is related to Y and Y is related to Z. This means that X has taken more credits than Y and Y has taken more credits than Z. We can conclude that X has taken more credits than Z, so that X is related to Z. What we have shown is R has a transitive property, which is defined in this definition, and we get a chance to be seeing this. And there's an example, which once again, I won't go through in detail. Well, then we can start combining these relations. And this gives some interesting characteristics. And I'll have a chart in 2 slides forward that maybe this will help you to be thinking about this. So given two relations, R1 and R2, we can combine them using basic set operations to form new relationships. And so here are some possibilities that they're having us to think about. What about composition? So suppose R1 is a relationship from A to B and R2 is a relationship from B to C. Then the composition or composite of R2 with R1 is a relationship from A to C. And so this is the chart that I was looking forward to getting to. So we can show a relatedness from here, which is R1, all the way over here. And so thus using this perspective, we can go from A to C, and there's like an invisible interim state that we don't necessarily need to be thinking about. And so as a black box, we can go from A to C. And so this is a way of thinking about composites of relationships. We could have multiple internal states, and that's going to be a concept that we'll be seeing on multiple things that you'll be covering in many areas of future classes and what you'll see professionally. We can also have the powers of a relation, so let R be a binary relation on A, then the power R to the nth power of the relation can be defined inductively, like you have a base step, which was R to the 1 is equal to R, an inductive step, R to the n plus 1 is equal R to the n times R. And you can see some more information in the textbook for that. Then we have a theorem, the relation R on a set of A is transitive if and only if R to the n. Well, you can just read this equation here and see what we're trying to get at. Okay, now let's go into section 9.3 and think of the different ways that we can be representing them. And there's two ways, matrices and digraphs. Matrices will be using a matrix that either has 1 or 0. So either is a relationship from one to the other or not. And digraphs, it's going to be probably a little bit easier for you to conceive relationships by seeing an illustration. And this gets into graph theory, which some of you may find quite interesting. And this will be one of the areas where you get a little bit of a heads up on that. We also talked about trees before, that gets into some aspects of that too. So in this section and in the remainder of the chapter, all relations we study will be binary relations. So keep that in mind. Because of this, in the section and the rest of the chapter, the word relation will always refer to a binary relationship. There are many ways to represent a relation from finite sets. As we talked about in section 9.1, one way is to list its ordered pairs. Another way to represent a relationship is to use a table. And this is something that you can see example 3 in section 9.1 in Rosen for an example. In this section, we will discuss two alternative methods for representing relations. One method uses a 0-1 matrix. The other method uses a pictorial representation called directed graphs, which we'll discuss soon. So generally, matrices are appropriate for the representation of relations in computer programs. That's the easier method for programming programs in computers to do computational things with them. On the other hand, people are often find the representation of relationships using directed graphs more useful for understanding the properties of these relations. So what do we do if we want to be using matrices? And so this just gives a little bit of background for that. A relation between finite sets can be represented used as 0, 1 matrix. That's going to be the thing that we're going to be thinking about. So here is an example of a 0, 1 matrix, and this is an example from Rosen of how we would be going from one to another. um, Here is another example of one of those graphs, and where we want to be thinking about how we would be doing a solution for this. And if there's a 0, there's no relationship between the elements that you're going to be utilizing. If there is a 1, then there is a relationship. And so here is a unity matrix. You can see that here's an example. All the main diagonals are 1 and everything else is 0. So there's a relationship between only one of these pairs when we have this. So if R is reflexive, this is the way it would look like. If R is symmetric, if and only if m to the m of ij is equal to 1. And so basically, you're going to see that there needs to be on the same level up here, it has to be balanced with the same number here. So if you have a 1 up down here, you can have a 1 up there, vice versa. Anti-symmetric means that you would have this kind of relationship, and so it's reversed. And so those just gives you one of the ways that might be a little bit easier for you to intuitively see how this is operating. So suppose that the relation R on the set of a matrix is represented like this. So you can be seeing it that this is a symmetric matrix. And so this is what they're implying and getting at with the solution as well. Okay, so that's the first way of representing. The second way is with digraphs. And so what this means, if you're going from A to B, that there's a relation to go from there. Here we have the going back into B. We have D going to B, B going to A, and vice versa. And so this is all of these relations that we're showing here graphically, and it's a lot easier for us to grasp that entirely with us looking at it visually. So we have an example there. Here we have another example. Here we're given the graph, and then we wanted to figure out the order pairs, so we can go both ways. So how do we determine which properties a relation has from its digraph? We can be looking for reflexivity, symmetry, anti-symmetry, and transitivity. And so I'm going to have several examples here that I can quickly go through, and you can see this. And so first, reflexive, no. Symmetric, yes. Anti-symmetric, yes. Transitive, yes. And so there's trivial cases, there's not a whole lot of connectedness. And so that's what we get for this first example. Now we have one that's a little bit more complicated. Reflexive, no. Symmetric, no. Anti-symmetric, no. Transitive, no. And so there's not a lot that are going on. And you can see the justification for each one of these here. Just feel free to pause the video and think about that some more. Okay, here is a third example: reflexive, no. Symmetric, no. Anti-symmetric, yes. Transitive, yes. And so we can be seeing how that works. There are no loops, so it's not reflexive. Symmetric, no. For example, there is no edge from C to A. Okay. Anti-symmetric, yes. Whenever there is an edge from one vertex to another, there is not one going back. And transitive, yes. Finally, here's a fourth example: reflexive, no. Symmetric, no. Anti-symmetric, yes. Transitive, yes. And so there are no loops. That's why it's not reflexive. There is no edge from D to A, so it's not. That's one example that's showing that it's not symmetric. Anti-symmetric, yes. When there is an edge from one vertex to another, there is not one going back. And transitive, which is trivially in this case, there are no two edges from the first edge at the vertex where the second edge begins. So those are just some examples of digraphs, and hopefully that gives you a little bit more perspective of how this would work. I'm not going to go into this in much detail, but here's an example of the powers, r squared, r cubed, and r to the fourth. So the pair xy is in r to the n if there is a pair of length n from x to y in r, which is following the direction of the arrows. So I'll just refer you to Rosen to get some more insight into this, but you've seen a couple examples of how to represent these relations in matrices and digraphs. That's the main point I wanted to have you capture from that section. What about equivalence relations? This is what we're going to talk about, equivalence relationships, equivalent classes and partitions. So in some programming languages, the name of variables can contain an unlimited number of characters. However, there is a limit on the side of character size, the number of characters that are checked when a compiler determines whether two variables are equal. So this is what we're getting at, trying to figure out equivalence. For instance, in traditional C, only the first 8 characters of the 8 of the variable names are checked in the compiler. These characters are uppercase or lowercase letters, digits, or underscores. Consequently, compilers consider strings longer than 8 characters that agree in their first 8 characters that are the same. That would be a limitation. Let R be the relation on the set of integers of characters such that one sample, I'm just going to skip over this. I was trying to think of some examples of what we might be able to use, but I'll let the charts help us out with that. The integers a and b are related by the congruence module 4 relation, where 4 divides a minus b, and we will show later that the relation is reflexive, symmetric, and transitive. It is not hard to see that it is related to b if and only if a and b have the same remainder when divided by 4. It follows that the relation splits the set of integers into 4 different classes. Okay, so I'm just trying to give a little bit of perspective, some of the things that you can read up in Rosen. When we care only what remainder an integer leaves when it is divided by 4, we need only to know which class it is in, not the particular value. So these two relations R and congruence modulo 4 are examples of equivalence relationships, namely relations that are reflexive, symmetric, and transitive. And so in this section, we will show that such relations split sets into disjoint classes of equivalent elements. Equivalence relations arise whenever we care only whether an element of a set is of a certain class of elements instead of caring about its particular identity. Okay, so that's a little bit of an overview of what we're going to cover. Let's get into some of these details. We have some definitions. A relation on a set is called an equivalence relation if it's reflexive, symmetric, and transitive. And I was trying to mention those terms in the introduction. Definition 2, two elements A and B that are related by an equivalence relationship are called equivalent. The notion A is roughly B is often used to denote that A and B are equivalent elements with respect to a particular equivalence relation, like the first 8 characters, what I was talking about. Okay, for strings, suppose that R is a relation on the set of strings of English letters such that A are B, if and only if LA and LB, where LX is the length of the string X, is an equivalence relationship. Show that all of the properties of the equivalence relation hold, and you can read through these here, or I refer you to Rosen to see that. Well, what about a congruence module M? So you can think like, say, if I was to say 10 minutes or 70 minutes, if it was modulo 60, they would be the same. So let M be an integer with M greater than 1, show that the relationship R such A comma B with this A is equivalent to B modulo M is an equivalent relationship of the set of integers. So you can walk through that definition, but using my analogy of just thinking about how we handle time, and we, without thinking much about it, can use modulo 60. Maybe that will help you to get some perspective on what we're trying to address there. Show that the divides relation on the set of positive integers is not an equivalence relation. Well, I'm not going to go through this, but you can read this and you can see how it doesn't satisfy all the things that we have in terms of reflexivity, symmetric, and transitivity. For equivalence classes, let R be an equivalence relation on a set A. The set of all elements that are related to an element A of capital A is called the equivalence class of A. The equivalence class of A with respect to R is denoted by A square brackets R, as you can see there. Only when one relation is under considerations can we write A without the subscript R for the equivalence class. All right, I'll let you just review the rest of this, but this is just trying to give a little bit more insight into equivalence. We have equivalence classes and partitions. In theorem 1, let R be an equivalence relation on set A. These statements for the elements A and B of capital A are equivalent. And we have some aspects of the proof, and you can also see the text for more details. So keep that in mind. Well, we can partition a set. A partition of set S is a collection of disjoint non-empty subsets of S that have S as their union. In other words, a collection of the subset A sub I, where I is an element of capital I, where I is an index set, forms a partition S if and only if we have these following relations. And you can see that each one of these, they're not overlapping, so each one of them has a certain number of elements in a set, and so we've been able to partition it into each one of these capital A elements. So we can have an equivalence relation partitions a set. Let R be the equivalence relationship on a set A. The union of all equivalence classes of R is all of A, since an element of A of capital A is its own equivalence class, A sub R. And so in other words, we have this relationship. And so from theorem 1, it follows that these equivalence classes are either equal or disjoint. And you could see these equations. Therefore, the equivalence classes form a partition of A because they split A into disjoint subsets. So here we see disjoint subsets, and so we're getting a chance to see this a little bit more there. Okay, I'm not going to go through this proof. Here's theorem 2. Let R be an equivalence relation on set S. Then the equivalence classes of R form a partition of S. Conversely, given a partition as we talk about here of the set S, there is an equivalence relation R that has the elements A sub I, where I is an element of capital I, as its equivalent class. So that's some additional information that we want to be thinking about as we're going through this chapter on relations. Now let's get into partial ordering. Here are the things that we're going to talk about. We're just going to be talking about the first three: partial ordering and partially ordered sets, lexicographical ordering, and Haas diagrams. So we often use relations to order some or all of the elements of sets. For instance, we order words using the relation containing pairs of words X and Y, where X comes before Y in the dictionary. We schedule projects using the relation consisting of a pair X and Y, where X and Y are tasks in a project set that X must be completed before Y begins. We order the sets of integers using the relationship containing the pair x and y, where x is less than y. Then we add all of the pairs of the form x to these relations. We obtain a relationship that is reflexive, antisymmetric, and transitive. These are properties that characterize relations used to order the elements of sets. Okay, so we're going to be talking about ordering, and then we're going to get into Haas diagrams to have us think about these concepts. So we'll have first a definition. A relation R on a set S is called a partial ordering or partial ordered if it is reflexive, antisymmetric, and transitive. A set together with a partial ordering R is called a partially ordered set or poset and is denoted by S, R. Members of S are called elements of the poset. So here's an example, show that the greater than or equal to relation is a partial ordering on the set of integers. So these properties all follow from the order axiom of the integers, which Rosen has in Appendix 1, and I can refer you to that, and you can read the reflectivity, antisymmetry, and transitivity comments that we have there. So we did this for the first example. Now we needed to evaluate all three of these things: reflexivity, antisymmetry, and transitivity. We show that the divisibility relation L is a partial ordering on the set of integers. And I'll let you see the rest of that. Here is another example that you can read. I'm not going to go through that, but just let you see that, and you can pause the video and look at it in more detail. So we have three more definitions. So first of all, for comparable, the elements A and B of the poset are comparable if we have this relationship or that relationship, where A and B are elements of S, so that we either of those relationships, we have a NOR between them, then A and B are called incomparable. So the symbol that we have here that's used several times is used to denote the relationship in any poset. So we're using it again here in definition 3. So if we have this as a poset and every two elements of S are comparable, S is called a totally ordered or literally ordered set. And this relationship is called a total ordering or a linear ordering. A total order set is also called a chain. And finally, we have this relationship again if it is well-ordered set, and if it's a poset such we have this is a total ordering, and every non-empty subset of S has a least element. Okay, lexicographical ordering. So given two posits, the lexicographical ordering A1 cross A2 is defined by specifying that A1 comma A2 is less than B1 comma B2. That is, then we have this relationship and some more caveats there. And so this definition can be easily extended to the lexicographical ordering on strings. And you can refer to Rosen to get some more insight on that. So for an example, consider strings of lowercase English letters. A lexicographical ordering can be defined using the order of letters in the alphabet. This is the same ordering as that used in dictionaries. So this is lexicographical order is definitely something that we're going to be using when we get into sorting problems, when we're thinking about this from a computer science point of view. Okay, the last thing that we'll talk about for this lecture is Haas diagram. So a Haas diagram is a visual representation of an ordered pair that leaves out edges that must be present because of the reflexive and transitive properties. So a partial ordering is shown in A. You can see that of the figure above. The loops due to the reflexive property are deleted in B. and the edges that must be present due to the transitive properties are deleted in C. The Haas diagram for the partial ordering A is depicted in C. So I'll leave it up to you if you find this a useful way of thinking about it. It can make the diagram a lot less busy. And so either you can be thinking of it as we're shown in A, or the Haas diagram version is over here. You can see Rosen for more details of the procedure for constructing a Haas diagram. So to represent a finite poset, using a Haas diagram, start with the directed graph of the relation, remove the loops, remove all the edges, arrange each edges so its initial vertex is below the terminal vertex, remove all the arrows because all the edge points upward towards their terminal vertex. And that's what we did to go from A all the way to C. All right, well, thank you very much. That's all we're going to be covering for this lecture.